Alright guys, today we're going to look at deriving a couple of equations that will help us solve kinematic problems. I'm going to start off with the two definitions we have for our course. We know that the average velocity of an object is equal to its displacement divided by time. We know that the average acceleration of an object is its change in velocity divided by time. If we draw a velocity time graph, just a generic one, like we've looked at, I'm going to show you how we can get some information from this graph. All right, so imagine this is the time axis, measure it in seconds, and this is velocity in meters per second. Let's say we started here at 0 speed at time equals 0. If we increase our velocity at a constant rate, it would look like this on a graph, where we would see, we think about 2 points on this line, 1 and 2. In order to get from this point to this point on our curve, we'd have to go up some distance, and we'd have to go over some distance. This change along the y-axis is our change in velocity, and this change along the x-axis is our change in time. If we remember that the slope of a line on a graph can be defined as its rise over its run, we get our slope is equal to delta v over delta t. We notice, though, that matches our definition for acceleration. Therefore, the slope of this graph equals acceleration. So, based on our graph alone, we've come to the conclusion that the change in velocity over change in time, as given by this straight line, is right here in this equation. And we can say that a straight line has constant acceleration. And that's important. Remember, in our word problems, we're always looking for this idea that our acceleration is constant over the entire time interval. If acceleration is not constant over the time interval, we have to break the problem up into sections in which the object is experiencing no acceleration or constant acceleration. Okay, now why did I take the time to show you this graph here? Well, if we look at that slope of this line, we can write it as such. A is our slope, right? Times time, delta t, is equal to delta v. What I've done is I've just taken the delta t from here and moved it over by multiplying both sides of the equation by delta t. If we remember the triangle we use in physics, that triangle means a change in the variable that's next to it. So how does velocity change? Changing velocity is defined by our final velocity by our initial velocity. So we're looking for the difference between the two values. I'm going to be interested in figuring out the final velocity of an object. So I'm going to take this initial velocity and move it over. So I'm going to do that by adding this vi to both sides. And if we look, I'm going to write this full equation. Instead of calling it vi for initial, I'm going to call it v naught with the little zero that you've seen me use before. I'm going to say that our final velocity is equal to, well, I've added the vi to both sides. V naught plus a delta t. So this becomes our first equation of motion. Okay. What this says is our final speed will be equal to whatever speed we started at plus the additional speed we gained from accelerating over the time interval. And we can figure out what our final speed is as long as we know these other variables, or figure out any other variable as long as we know the other three. So this is the way we kind of go about these derivations, if you will. We look for relationships in a graph and write them as a mathematical function. If instead I looked at a graph in which I have time down here, I have velocity in meters per second. If instead I didn't start at 0, let's imagine a situation where I had an initial speed, but I accelerate constantly. I can imagine this scenario being very similar to something we looked at last week, in which to determine the displacement of an object by looking at the area under the curve. Well, I can break this into two separate areas. This is the area of a rectangle, and this is the area of a triangle. So let's figure out what's going on here. Let's look at the dimensions of these. And just so we're clear, I'm going to put it like that. So from this point to this point, this is our base. This is the height of the triangle. And this is the height of the rectangle. So I'm going to put HT for triangle, HR for rectangle, base. So what is the height of the triangle here? That's from this point to this point. This is a change in velocity. This is going from some velocity initial to some velocity final. This is a change in velocity. What's the base of that triangle? So the base of the triangle is the same as the rectangle, right? And that's just your change in time. So we can think about this area between the rectangle and the triangle as being the total displacement of the object. Let's come down and write it. We're going to say our displacement, delta x, equals the area of that rectangle plus the area of that triangle. I'm just kind of writing it in shapes. So now we're going to look at what each one of those areas is. So our displacement is equal to the area of the rectangle will go from 0 velocity to some new velocity. Okay? I'm sorry, from 0 to initial velocity. This is where we started. The y-intercept is where we started. So let's write that. That's v naught minus 0, which is just v naught, times delta t. I'm going to add it to the area of this triangle. Plus, we have this height, this base. So we know that's 1/2. The base is delta t, and the height is delta v. When I see this equation here, I notice I have a delta v, which also appears in my equation at the top, our definition for acceleration. I can write delta v in terms of a and delta t. Again, we can rearrange this to say a delta t is equal to delta v. And since a delta t is delta v, I can plug it into this equation here. Just going to rewrite the whole thing now. We'll get delta x equals v naught delta t plus 1/2. Well, delta t stays, and I'm going to substitute an a delta t. Now I have two delta t's and an a, so that's an a delta t squared. This is our second equation of motion. And it tells us that the distance an object moves relative to where it started will be equal to its initial speed times the time interval, so just the distance it gains from moving at some speed, plus the additional displacement it will get due to its acceleration over that time interval. Distance equals distance plus distance. So one thing we're moving, that's like if I was moving in this direction and not accelerating, I would have swept out just the area here. That's the displacement I get just from the act of moving. And this is the additional distance I gain as I move in this direction but I accelerate when I'm doing it, sweeping out both these regions. So this becomes our second equation. Now I'm not going to derive the third one for you. It's just a little bit mathematic-y, but I will write it so you have it. That equation tells us that the velocity of an object will be equal to its initial velocity plus 2 times its acceleration times its change in position. The difference is with this formula, these velocities are squared. Other than the squared variables, though, it's pretty much just straight basic algebra like we've seen in the past. This equation is the one that I think is most unique because it will allow us to solve problems in which time is not a variable. If we inspect all three of these equations, notice in our first equation we looked at, we have the final velocity as a function of initial velocity, acceleration, and time. 4 of our 5 kinematic variables. Here we have displacement. Displacement is being described in terms of just the initial speed. Notice there's no final speed in this equation. We have our time interval and acceleration. This equation looks at both of our speeds, just like this equation, and also considers acceleration and displacement. Delta t does not appear in this expression. So recall we have 5 kinematic variables. They are delta x, our initial speed, velocity, our final velocity, our acceleration, and our time interval. Our goal is to always try and find 3 of these 5 variables to solve any problem. So these are the equations we use. Number 1, number 2, and number 3. The goal, and game if you will, is to figure out which combination of equations will allow us to completely describe the motion of any object moving in a straight line.